Okay, so welcome back. We're very happy to have Krishnendu Sengupta from IICS Kolkata, who will tell us about dynamics and entanglement for conformal shells.
Okay, I'd like to begin by thanking the organizers for inviting me here. And at the outset, let me just tell you that I'm just a poor condensed matter guy. I don't really work in field theories and that kind of thing. This is really the work of all my collaborators. I'm simply presenting it. Two of them are in the room, Kaushik, from whom I learned almost all of this, and Boishali, who has been working with me on certain projects. So any questions should be all directed to them. So that's okay. So and these are the publication in case any of this work seems interest. So here is a brief outline of my talk. So first I'm going to start with driven CFTs, and for introduction, just talk a bit about correlations, energy densities, and that kind of thing in a driven CFT in 2-dimension. That's a anyone thing. This branch of work actually followed what was started by Zueda, Wen, and others in a remarkable paper, which showed that driving CFTs are indeed possible, and these are a very interesting set of results. And then I'm going to talk about how to generalize this in a higher dimension. And this is the work that I did with Sumit, Diptarko, and others, Arnab Kundu. And then I'm going to shift gear a little bit, talk about entanglement in driven CFTs. And finally, if I have time, I'm going to talk about a quantity known as entanglement asymmetry, and we'll just show that it's possible to calculate this in a given 2D CFT. And it gives some interesting things. So that's sort of the outline. So first, let's talk about 2D given CFTs. So in the dynamics community, in which I've done some work. So whenever people talk about periodically driven systems, and I'm going to talk about periodic drives only, the interesting thing to compute is its Fluke-Hamilton, because that that essentially controls the properties of the system at stroboscopic times. And by stroboscopic times, I mean that when time is an integer multiple of the drive period. And the reason is that because of this periodicity, the evolution operator at the end of any integer number of drive cycles, n times t, is simply given by this Fluke-Hamiltonian times n times t divided by h. Okay, so that's a generic thing. So once you know the Fluke-Hamiltonian, you know all the properties of the system, modulo the initial state, of course, up to because you know the evolution of it. So the natural thing to think is that what happens when I try to apply this drive to conformal field theories. So the point is that once you drive a CFT, the natural thing to assume is that because you are putting in another scale in the form of either drive amplitude or frequency, it's going to deviate away from this CFT and move away. Okay. Now, this is natural, but however, it was, and this is Zueda Wen's work, that this is not always a true. And the class of CFTs can be taken out of equilibrium without performing the conformal inference. Okay. That was the first thing which got us motivated into working on this. And specific examples of such CFTs are ones with sine squared deformation. These are the ones where your Hamiltonian can be written in terms of this Virasarus, but it's not only L0 which is involved, but there is a combination of L1 and L-1 which also comes. And this phi, or you could put a number here, that's the deformation parameter. Okay. And just to set the stage right, these are the standard, commutations of these Virasarus, and they can be written in terms of the traceability tensor, which is standard.
So you would also have only doing that. And six as that calculations too.
For now, I'm going to go to higher, and there, of course, I'm not going to talk about this Virasarus, but other operators and stuff. Okay, so the basic thing that Zueda and others sort of use to do this dynamics is that they notice that this Virasarus generators forms an SU11 subalgebra. Okay, that's the standard commutation out here. And a 2D representation of this algebra can be written in terms of standard Pauli matrices. And notice there is this thing that, the Hamiltonian now, which was something like this, some linear combination of L0 and L1 and L minus 1, can now be written in terms of some sigma z, which comes from, comes from this L0. And this L1 plus L minus 1 gives a I sigma y. And this I essentially is because it's a SU11. And f of t is something that I'm going to drive. And so I'm going to make this thing time dependent. Notice that the instantaneous, so what do? You now try to calculate this evolution operator, which means that you are going to Trotter decompose this and break this down into infinitesimal time steps. At each of these time steps, the instantaneous Hamiltonian, and therefore one can show, because of this structure, U and HF is still described by a CFT, that is by an SU11, this thing, which you can map back. So this is useful to get your Fluke Hamilton.
So can I ask a night?
Yeah.
So if you go back one slide.
One slide.
Yeah, so you have this Hamiltonian where there's this parameter theta, and that of course you can vary uniformly. So let's say I just think of an Ising's CFT. You said that h of t at each instant of time is a CFT. So with this theta, what is it good?
No, this theta is what I'm making time dependent. Even this phi, right?
Oh, sorry, this
So this is what this parameter is precisely what is made time dependent. See, if you just had one parameter in your theory, there is nothing you can make.
No, I understand.
Yeah.
You made the statement in your slide that h of t.
So at every instant,
Right.
h of t is still given by this form.
Right.
This is a CFT Hamiltonian. And because of this SU11 structure, I can show that U also can be written as some e to the power IHFT, where HF has this particular form. So it's still given by these three generators L0, L1, and L minus 1. It doesn't go away from that, or it doesn't, break this conformal. Let me just do this, and then one can probably see this more clearly. Okay, so the evolution operator can be written in the following form. And and this then can be analytically continued to real time. So every time when we are going to do this, we are going to work in imaginary time and then analytically continue to real time at the end of the calculation. So, and also, then the question is that how would the operators of the CFT transform? And apparently it's just a coordinate transformation with some derivatives, which was shown in this paper. But this is, the general thing, because this kind of evolution essentially goes to a transformation, a modular transformation like this. And this ABCD essentially determines all the properties of the theory, and these coefficients carry the information about the drive. Okay, so this information is sufficient to compute any 2 and 3 point correlators of the driven CFT, and I'm going to do this for the, just show this for the kind of drive that I just showed. So that's the idea.
So in this CFTs, the primary operators can go to another, like
No,
are they good quantum numbers?
What do you mean by quantum number? So if I have a primary operator, so let's say that I have a representation in terms of z and z bar. Under this drive, it just goes to some new coordinates times some prefactors. That's the transformation that I did. Because you see, at the end of the day, what am I going to do? I'm going to compute these correlators, right? And these correlation functions of primary operators, I know how to write them, at least for the 2 and the 3 point. I mean, 4 and a higher, I'll have to do something else, but forget about that. And then I will use this coordinate transformation to write the new dynamical correlators. That's the game. Okay.
So it is the U that drives your conformal transformation in some sense. So
it is the U which gives the periodic, it's the U which is the evolution operator for the periodic drive. Okay. And the question I am asking is that what happens to the operator? This is sort of the Heisenberg picture. This is the Heisenberg picture. Is that okay? So, but before doing that, let's just talk about these dynamical phases, because a general SU1 Hamiltonian one can write it in terms, sorry about this change of notation, these are just L0, L1, L plus and L minus, okay. It turns out that there are dynamic phases of this Hamiltonian, and the way it happens is that once you have this evolution operator, which is in form of this matrix, you can compute the trace of this matrix. And when this trace becomes greater than 2, this phase is called the heating phase. For example, this is characterized by a linear growth of entanglement and any other correlators.
Growth with respect to time.
Growth with respect to time, of course. Stroboscopic time, if you want to be more specific. Then there is a critical line where this thing becomes exactly 2. Okay, just becomes the identity matrix. And this logarithmic growth of entanglement. And here in the non-heating phase, when is the usual phase where tracing is less than 2. Here is the standard unitary transformation in this presentation.
Why do you call it heating? What is the connection?
Okay. So that is because, okay. So I should really say, okay. The reason why we call it heating is that when we drive a standard quantum system, your entanglement grows linearly with the drive. And that is associated with the spread of the initial state in the Hilbert space. And that is colloquially called heating in the dynamics domain. And that's how I actually understand the name, but I mean, there may be other interpretations. But more formally, this is called the hyperbolic phase, the parabolic phase, and the elliptic one. And this has to do with the sign of the Casimir of this Hamiltonian. When the Casimir becomes negative, it goes to the parabolic phase and so on. So there is a whole geometric interpretation of all this.
So the EU has only the ideal converge of theory.
No, so if you do this, and because there is this, because it's SU11, there is this factor of I, it's not always the phase. These are phases when you are in the non-heating phase.
Whatever you have said so far.
Yeah.
Where has it been used that it's a periodic?
When it's a periodic drive?
No, I'm saying at that you are only looking at periodic evolutions.
Yeah. Oh, that's because, no, not yet, but the point is I'm going to come to that in a moment. Because when I'm going to evaluate these correlators, I'm going to use the Fluke Hamiltonian and use its property. And then I'm going to say that, and that's where periodicity.
I'm saying this because in a typically in 2D, since 1 plus 1 2D, then any time dependence in the Hamiltonian
Okay.
can be traced back to something called a conformal factor in the
Sure.
metric.
Yeah, sure. No, for quench, we know that can be done. But this is the one for the periodic case where, let me just go ahead and then see.
Points of time that one is in the space-time, space-time, the Z part. Z has to come for
Sure.
All of that is
Right. The other is the drive.
This P is essentially a parameter.
That's a drive period.
This is a parameter group.
Yeah, that's a drive
This
period.
is different than the space-time
Of
stuff.
course, yeah, sure. That's a drive period. That has nothing. And one of the simplification that occurs when you do this, that you are, you identify this T especially at those points. And that's what allows you to do this calculation.
But you are not going to fix this T, gauge fix this T with one of the space-time, like the tau coordinate of the Z.
No, I'm going to evaluate.
Are you going to identify that? Whenever we associate target space and
No, this is different. No.
Yeah,
Yeah, you heard a question.
So the thing is, how important is it that you add the term which is like the L plus 1, L minus 1?
If you-
Principle can have formula and use that.
No, in principle it can, but the point is that we were coming from this point of view of the deformed CFT Hamiltonians, and usually they are with L1 and L minus 1. In principle, you can do this with LQ and L minus Q, and it's a bit more complicated analytically, but there is also this simplification, which is that those are not going to keep the CFT vacuum invariant. Okay, L1 and L minus 1 does. And so this Hamiltonian, if you start from a vacuum, it doesn't do anything. So you need to do something else. I'm going to come to. So that's one crucial difference, but otherwise you can use them.
I have a confusion related to the question that.
Yeah.
So this time, I presume is the time of space time, right?
No,
Because
see the
otherwise you will not get that, the transformation that you showed.
no. So let me just get to it. So
It's not a parameter in the Lagrange, or am I wrong?
no. Capital T is a parameter of your Lagrange
Achha.
because you are driving.
Achha.
Okay, and that's the drive period. Small t is the actual time. Okay. Okay, so now with this cosine drive protocol, what happens is that to compute the Fluke Hamiltonian, even for this 2x2 matrix, is I mean, it's impossible exactly because you don't have unlike the square pulse and other protocol, but one can do some perturbation, and that's perturbation is what I want to show. So we are going to use we are going to be in a situation where the drive amplitude F naught is quite large, and the other terms in the Hamiltonian is smaller compared to this. Then to 0th order, if I just keep only this term in my Hamiltonian, I can find out my U naught exactly. That's a trivial listing because it's only one sigma z, and it's really trivial. And from that, I can identify the first term of this Fluke Hamiltonian HF0 to be this. Now, there is of course more terms, and at least I need to compute to first order to find out what the effect of this L1 and L-1 is. And so to do that, there is another thing that there is an exact symmetry of this Fluke Hamiltonian, or rather the evolution operator, is that because of this structure that it has only sigma z and sigma y, sigma x anticommutes with, sigma x anticommutes with HF. I'm sorry. Yeah. Sigma x anticommutes with HF, and in fact, you can show that sigma x just give you U inverse, and therefore, HF must be of a form which only has sigma z and sigma y. It cannot have a term of sigma x. Okay. Now, with this knowledge and some perturbation theory that you can carry out, the first order perturbation theory, you can pin down what this U is. Okay. And it turns out that this U has a reasonably simple form. It has a term which is proportional to sigma z and a term which is proportional to sigma y. And then there is this nx and ny, which are just like a normal normalization vector, a normal vector, components of a unit vector actually. And this alpha, which has all the information of these dynamics, can be computed in terms of these Bessel functions. This is a simple calculation. One can do it in a page, but I just give you the final results. But now, if I sort of take the trace of U and try to find out these phases, this is the structure that I got. Now, first of all, this follows from exact numerics, which is really exact because we just diagonalized everything numerically and families. And this is the first order analytic calculation, which came from this expression. They are more or less qualitatively similar. Okay, and you clearly see that there are these red and violet regions, which is this heating and non-heating phases, where trace U is less than 1 or less than 2 or greater than 2, and in between there are these lines, which has this, the parabolic phase. Okay, so the point is that okay, so you see that when this delta F times T is some integer multiple in units of pi over L is some integer multiple of n naught over 2 integer. Therefore, one term of this sum will blow up, and therefore these are the points which, and therefore this means alpha is much greater than 1, and alpha much greater than 1 essentially means that you are in the heating phase. Okay, because you see this theta becomes imaginary, and the so U1 is not, so U1 can be written in terms of cosine and sinh rather than cosine and sine. So you see that you are right in the middle of the heating phase, and these are essentially the midpoints of these blocks, okay, these red regions. And alpha equal to 1 is where trace U becomes equal to 2. Because if alpha is equal to 1, you see that, with all this, you just see that there is no, so this thing one can show that trace U just becomes equal to 2. There's a simple calculation from here, and those are these lines. So yeah,
ends blowing up, right?
No. There is a theta here which has this square. So yeah, one is to be a bit, yeah. Sure.
So this is
Yeah, I was going to ask. It is independent of the CFT, this computation. Doesn't matter.
Yeah, sure.
But why? This is what.
Oh, it will come in. So when you do this correlation,
Uh-huh.
if you do 4-point or other correlations, then the details of the CFT is going to come.
Okay. But not even the dimension of the operator comes into this.
It will. I haven't computed anything as yet.
I
No correlation, no energy density.
Okay.
Those are going to come, and they are the operator dimensions are going to come.
Okay.
This is just the evolution operator, just the dynamical part.
I see. Thank you.
Sure. I mean, this could as well have been the dynamics of a spin in an imaginary magnetic field. Same thing.
So this is in the Heisenberg picture, right?
Yeah, I have just computed U as of yet. I haven't done anything with the operator. So, but I'm going to work in that.
In terms of this kind of spreading the peak and the scale.
Yeah. I'm going to show that in a moment. You can. I mean, there is an exact correspondence, but it's simpler to work in the Heisenberg picture in terms of coordinate transformation. That's it. Okay, so now I'm going to come to results. Okay. So the first thing I'm going to compute is something that we do in the condensed matter community a lot, which is called the return probability, which says that I start from a given state, I drive it, and then I see what's its overlap with the initial state. Okay. That's the return probability. And here, the first input of the CFT comes is that I have to choose an initial state. Now I cannot choose the ground state because that would be trivial, because you essentially acting on the ground state just gives identity. Therefore, I'm going to choose one of the primary states, defined by some primary field. And there the dimension of H and H bar is going to come. Okay. And then the overlap amplitude computes the overlap of this state with this time translated version, and that's given like this. Okay. Now this computation is simple because it just constitutes computing correlator of two fields, phi coming from the gate and phi coming from the bra, and then taking proper coordinates. Is the one from the k goes to infinity, the one from the bra goes to 0, and you need to do this, and it's a reasonably simple calculation. But at the end of the day, the result is amazingly simple. It just depends on this coefficient am. If you think about it, times some conformal dimension of the state that you are. And if you think about it, it cannot depend on anything else because, I haven't really put in a proper correlator here. These fields are only in the sense of the state, and therefore, its primary dimension may come, but nothing else.
yeah, what is small.
Yeah, coming to that. So, let me just read. You see that I have this thing as U, right? So I can write this as A, B, C, D. That's 2x2 matrix. So let me just write it here. So U to the power n is written as An, Bn, Cn, Dn, with An, Dn minus Bn, Cn equal to 1. Those are the A's. These are just so whenever you see some A's, An's, Bn's, etc., those are just the coefficient of this 2x2 matrix. So I can compute this probability, and here you see the difference of the different phases. So in the heating phase, this is exponentially decaying at large m, and this n essentially means the number of drive cycles. Here, this is non-heating and it's oscillatory, and in the transition line, it's a power law. Okay. So this just tells you the way this overlap goes with. So if you plot the log of this overlap, and then you see this linear and then other. And this is, so I must say that when I say on the transition line, what I really mean is that I'm very, very close to the transition line, because exact determination of the transition line is a bit difficult because, it's complicated. This equation alpha equal to 1, of course, one can numerically determine it, but only up to certain precision. So I'm infinitesimally close to the transition line. Okay. The next one that I want to compute is the energy density, which is the expectation of the stress energy with respect to this given state, and a similar calculation. So as we know that if I'm on the complex plane, the stress energy gets is just this plus T of Z. So, and then I have to just do this computation after n cycles of the drive, and therefore is a
plane or sphere? sphere.
plane.
That means Mobius.
No. I'm on the complex plane. Z is the coordinate on the complex plane.
Plane of complexified CP1, right? Because you have Mobius.
No, so okay. If I start from, so here I start from the cylinder, I transform to the plane, do all my computations on the plane, and then get back to the cylinder. Okay, so that's the idea. So, okay, so this just needs the OP of this primary fields with the stress energy, which can be written down, and using this I can compute the energy density. And here is the answer. So here is something interesting that comes in, that you see that this En of x depends on this Q's, these factors, and these at large n are exponentially growing quantities, and therefore the stress energy density at any point in x, except for some special points, essentially decays exponentially, because there is a q1 to the power, well, there is a q4 and a q squared, so it's 1 over q squared. However, there are some special points which are given by this, where this q1 becomes almost equal to q. Okay, and at those points there is a peak that develops, and these are of course exact expressions when n tends to infinity. But as you increase your n, you see this pile up of energy density at specific point very clearly. And this delta x, the distance from the center of the chain, if you're thinking of a chain, compactified chain, is essentially tunable by tuning the drive amplitude or the frequency. It physically means that you started with a system which had flat density, okay, and a finite total energy. As you drive, although your drive is global, because of the conformal symmetry, there is a relation between space and time, and what it does is to just concentrate its energy at specific points. Okay. So this emergence of spatial structure is something that Ashwin and others pointed out in a long time back, but you also see this in this kind of
This spatial structure emerges in the non-heating phase, or
this is in the heating phase. I'm going to show the other phases in a moment. Yeah. In the heating phase. Yeah. It is more rapid in the heating phase, but you will see similar structures also in the other phases. Okay, not in energy density, but in correlations I'm going to come.
Sorry, can I ask?
Yeah.
So intuitively in CFT, I mean, we usually expect things to decay with power loss. The reason why there's exponential here, is it because there are two scales, the scale of the driving and the scale of the system size, or why is there some exponential?
Okay, the reason it is, why it is exponential. The reason it is exponential is because of the scale of the drive.
Right.
Exponentially decaying part.
Yeah. It's
okay.
It's the scale of the drive and
and
L.
at this special point, the system size and these two scales essentially play with each other to give you a situation where there is a pileup of energy consumption.
So is it just some energy conservation?
No, so you are driving, there is no energy conservation. You are putting in energy in the system, right? But the density, so usually what happens in standard condensed matter system is the drive is global. You don't mess up with the spatial structure. But here, because space and time is related by all these conformal symmetries, this thing happens. And that's what is a bit different for conformal field theories compared to other. Okay, so let me go to the non-heating phase. Here also the expression is roughly the same, except now, except now that, your cosine and sinh, okay, I can't really handle this, but your cosines and sins are got to cosine and sines. And therefore, the behavior is quite oscillatory. And here you don't see a pile up, your energy just flattens out as you increase. As you increase the number of reps. And it's reasonably slow, as you can see. I have to go to 50 cycles to get this plot. Whereas, in the other case, it was just 5 cycles and it was. And the interesting thing also happens when there is a transition line. Here, what happens as you approach the transition line from the heating phase, these two peaks just move towards each other. And exactly on the transition line, they're going to be just one peak at L/2. They're simply going to fuse. I'm not exactly at the transition line, I'm very close to the transition line, and you see that there are still two peaks. Okay, there were two peaks, and also the dynamics is reasonably slow because it's a power law thing, not an exponential.
Is it easy to compute analytically the asymptotic energy density in the regime where it just flashes
Yeah, you
out?
can do that.
Yeah.
Yes, you can. So actually, all of these are sort of analytical. There are analytical expressions of all of this in the paper. I didn't want to clutter my slides too much. Okay. And actually, so you see that this is the decay in the transition line. So that's like 1/n² decay as as you increase the number of layers. So let me move on. The other thing that you can compute is the unequal time correlation function, which is another completely non. And here the good part is that you can start from the ground state, because unequal time correlation function essentially means that even if you start from the ground state, you are going to sort of access the excited states anyway, because it's unequal time, and therefore the result is not trivial. You still get a non-trivial result, unlike equal time correlation functions. So here what you do is the same thing. You just compute this, the 2-point correlator of the primary fields, which is again a straightforward computation. And it turns out that this correlator can be written in the following way. Here I have assumed that H and H bar are the same, and essentially these are the factors which are kind of interesting. So because you are computing it at some W1 and W2, you can essentially write it in terms of the center of mass and the relative coordinates out here. And it's this coordinates which enters it in this picture. So in the heating phase, what happens is that whenever your coordinates are such that the center of mass and the relative coordinates satisfy this, where alpha is of course that parameter that I showed you, you will see that there is a pile up. So this correlation function, unequal time correlation function, peaks at that point, because this thing blows up. And this is again at strictly true at infinitum, where sinh and cosinh are strictly exponential. But you approach that point very fast. However, there is also some there is also some divergence at the non-heating phases. So for example, in the non-heating phases, if your sine and cosine theta, they are theta equal to m pi, then you see that as long as x relative is 0, if this thing goes to 0, this will again blow up. So there are these lines where x1 is equal to x2, which are on top of each other, where they can blow up. But this is special. Otherwise, for a generic thing, they're going to blow up if this quantity is satisfied. So I'm going to. So this is the heating phase. This would be the blow up at the non-heating phase. And for the transition line, they only blow up when x1 is equal to x2 or minus x2, and that's the line circle. So and also the response is oscillatory in the non-heating phase, and it's a linear decay on the transition line. But the point of all of this is to just state that in all of these quantities, what happens is that although you are making a global drive, a 2D CFT, it completely changes the spatial structure of the field. And that's not normal in standard condensed matter that we are used to, because a global drive usually doesn't break spatial symmetry. So that's the point that I had. So now, let me, yeah,
Can I
sure.
think of this out of different time correlation function as a sum over high point correlation functions?
Okay, if you have this, you are certainly going to access. So, okay, the way we evaluate this is that typically when we think of this thing, is that you have a state, and then I have some x of t, and let's say x of 0, and then some other state. So what I'm going to write is something like this, right? And now, if you want to decompose, you decompose in this basis, and which means that it accesses all the higher states of the field. So that's the way I think about it. I'm not entirely sure, but also alternatively, you can expand this in terms of the full set of operators and try to do that. But I think these two are identical. Okay, so can I go to? Okay, so this is the second part of the talk. How are you doing it? Yeah.
One small thing. And none of this is going to depend on L, right? This thing that you're going to see. You're even given to super small businesses.
Well, okay. Lattice is a tricky thing. I'm strictly talking about conformal field theory. The moment you bring in lattice, there will be lattice corrections, and many of these things are going to go. So you have to be very careful, and particularly those are very strong if you are system size. So actually, in this paper, we also tried some this deformed CFT can be realized in fermions with some sine square potential on a chain. So we tried to take that and do this. And what we found is that we had to go to pretty big chains to see these kind of effects. So lattice corrections are very strong. Actually.
Very strong.
Yeah.
I think this effect that, the energy density kind of steals up.
Yeah.
If you kind of drive a lattice, small lattice, and I mean, I'm just asking your expectation today. So if you take a small lattice system, give it to a spirituality and drive it.
First of all, the divergence is going to be cut off. That one can probably see. Okay, now how much and to what extent this, this bunching would occur, that I think one needs to do and check. I haven't checked that, but yeah, one needs to do and check. And I'm pretty sure that you need pretty large size lattices. But that can be done because this sine square deformed theory is a free fermionic theory with a sine square potential. So it's not an interacting theory that cannot be simulated easily on a lattice. So.
As you see, if I globally break the systems of the spatial, it's in the coordinate systems, you don't see that the spatial symmetry that. But here, in CFTs,
Yeah.
So is it just because like the way you are driving the system, like you write that L0 plus L plus L1 plus L1?
See, so the point is that what I'm doing, think of this more in terms of a square pulse. So what I'm doing is that I'm driving the system, but with different Hamiltonians. Now, usually in condensed matter system, if you do it globally, the spatial structure of these Hamiltonians remain the same. But here, this is not the case because it's a CFT. You change Hamiltonian, you also change. And so the resultant thing has a spatial structure as well as a temporal structure.
I could have started with maybe some alpha T of L0, but not L1 plus. There I should not.
No, that's your. See, the point is then you're at every point, then your Hamiltonian is the same, right? Because it's just a sigma z, but you need two sigmas to give anything non-trivial. Okay, so let me go into this. So, once we understood these deformed CFTs in D equal to 2, we were trying to think whether there is something similar that can occur at D greater than 2. And of course, here you don't have Virasoro's and this local conformal stuff anymore, but you still have your the standard operators. And in terms of this, you can write down Hamiltonians, and the Hamiltonian that we try to work with are the ones where D and K and P, which are the analogs of L1 and L minus 1, are sort of superposed. Okay. And this pi mu is a projector because now I have essentially different mu's. Mu can go to 0, 1, 2, 3, whatever. And this projector just determines which mu I am using. So, no, not yet. I haven't done to drive it. I'm just taking a simple Hamiltonian, which is a linear combination.
Sorry. In principle, you could have taken a different projector for K and P separately. This is before you had different terms for each, no? Or
no, I was using L1 plus L minus 1, but you can in principle, you can in principle do that. You just have to make it Hermitian. That's the only thing. Okay. But, who wants to complicate life?
Yeah.
So what we have is there are D plus 1 different SU11 subalgebras here because this D, A, and P do have a SU11 structure. They have a SU11 subgroup. And so for all of this, I'm going to sort of work in imaginary time, take this SD cross T to RD plus 1 and work there. So let's just talk about these deformed CFTs in D greater than 2. So for example, if I just write this deform CFT, where these parameters are cosine and sinh, so I can choose this CFTs like this. Then, of course, I can design a similarity transformation out here, where I can map this entirely to a CFT whose Hamiltonian is just D. Okay, I can rotate it back. And this rotation, essentially what we have checked is that you can see that all of these this generators essentially goes to their prime values and they satisfy the same commutation relation as the original generators, which tells you that these deformed CFTs are kosher CFTs. You can sort of. But interestingly, when there is this other term, when beta is greater than 1, so okay, sorry, let me just. So beta is this parameter out here. Okay. So when beta is greater than 1, okay, this Hamiltonian has a sinh out here and the cosine out there. So it cannot be really mapped into a D. It can be mapped into a set of Hamiltonians, which is called Lusher-Mack Hamiltonians. And these Lusher-Mack Hamiltonians also have well-defined, energy states and all that, which I have written here. But interestingly, now using this, I can say that the Lusher-Mack Hamiltonian at some T, which is my drive, this thing, or here you can just say that it's some small time, T, is equal to the standard CFT, where D is your Hamiltonian, but in the complex thing, which means that when I compute U of T later with this Lusher-Mack Hamiltonian, I'm just going to get, this cosine and sinh, which is going to give me decaying response. So it seems that even in this higher dimension, it might be possible to essentially generate this heating and non-heating phases. Okay, so that was the first intuition as to why we wanted to do this.
Something that would be
Well, this is all very trivial. Yeah.
I'm just trying to ask if this is, if you can think about this in terms of I mean, just transformation where I mix my creation and relation operators.
Maybe I haven't really thought about that. Yeah, it might be.
Transformation in some sense.
It may be actually. If you have a bosonic, if you have this harmonic oscillator representation, yeah, it can be. I haven't thought about that, but it is possible. Lusher-Mack probably does that. Yeah.
Yeah, so that's the same thing.
By distance, does this look like something they can do? The second one is language.
So if you do the second quantized language, maybe it's done in the original paper. I don't remember right now, but then probably what you were thinking is correct.
Like,
they will.
Bogoliubov transformation has an SE11.
No. The Bogoliubov transformation doesn't take you from this to D. So these two are disconnected sectors. You have to be careful about that. You can. So once you are given this parameter beta, it's either less than 1, in which case you can map it to D, or it's greater than 1, in which case you can map it to this Lusher-Mack. But you cannot map from one to the other with the.
That is, but each of them will be sort of. I mean, one is sort of like you can have the sines and
cosines, and the other one is cosine and sinh. Yeah,
it will be crossing the light.
Yeah, that will be exactly crossing the light.
Parabolic and hyperbolic comes from that.
No, in fact, if you just do this theory at beta equal to 1, then you are going to see the light. Exactly. Right. Okay, so let me just move on. So now the next thing is to do, how do we do time evolution? Now, because this D, so we are going to think of this Hamiltonian in terms of a parameter beta, which is a linear superposition of D and mu and Kv with some projector out here. Okay, so this is my entire Hamiltonian. So now to obtain U, that is, this evolution operator, I need to evaluate this, and this is usually difficult, but here, because of this SU11 group, there is some Baker-Campbell-Hausdorff formula, which allows me to write this down. Okay, and these are essentially lambda naught, lambda plus, and lambda minus are things which depends on different parameters. Here, nu is square root of 1 minus beta square, where beta was that parameter through which you were tuning this. And this cosine and sinh, this W is essentially your deformation. This, in W is essentially the time at which this evolves, with which this goes.
I'm sorry. Okay, so this information is still a periodic.
No, I haven't done periodic times yet. So this is just a Hamiltonian evolution, and I'm going to tell you why I'm doing this in a moment. Okay. So now, knowing this, you see, I can now ask the question that how do my coordinates change? Because you see, in all of this dynamics of a CFT, in d equal to 2, the central point is that I could identify the coordinate change and therefore evaluate the correlates. So here the first question to ask would be how would my coordinates? And from here, I can do this explicitly. Okay, so I can use these operators knowing the form of the generators and essentially find out what these coordinates. This is a calculation that one can do. And okay, I don't want to do it again, but one can do this. So the point is
mu is just that
expression, that huge expression. Okay, so yeah, it's complicated. But now think of doing this for different Hamiltonians at different cycles, and this becomes very complicated and intractable very fast. Okay? So the idea is that do we use the SU11 structure of this, this subgroup property of this D, K, and P, and try to come up with a matrix multiplication scheme, just as we did it in D equal to 2, to obtain the change in coordinates. Okay, but of course the problem there is that we don't have a complex number out here, right? You don't have the complex plane anymore, and this is where Kaushik's knowledge came into came to help us. And it turns out that you can still write these coordinates in terms of these quaternions, matrices. So what you do is that you take associate each coordinate with an element of a matrix, which could be either identity or one of the Pauli matrix. Okay, and therefore you create this matrix which has your coordinate information. Now, which coordinate you choose to associate with the identity matrix is your choice, and it's arbitrary at this stage. And therefore, you can get a coordinate like this. Now, the next step is to find out the elements of U, which you can do using the SU11 property. And this is just minus sigma z plus I beta sigma x in my language. And you can just get this A1, A2, A3, A4. These are all matrices, the elements of this 2 by 2 matrix. Now, it turns out that the transformation of the coordinates can be captured by transformation of these quaternions, where the transformation is given by this. So this transformed coordinates are given by some q prime mu, which is related to the old q mu with this A1, A2, A3, and A4. Okay. So this people have looked at before, and there is a huge literature on this quaternion. And I of course didn't go through any of this literature. Kaushik just told me that this is the case. It was very convenient. So, but the point is that this allows you to write down the coordinate transformation.
But is it that this coordinate transformation is the right term?
No, it's not a Y transformation. No. So then what you can do is basically check, because now I have this method of computing my coordinate transformation and I know the exact result, and we can do a few lines of algebra to see that they matches the BCH form. But the point is that this gives you a hugely simplified way of evaluating these coordinates. And notice that in principle, I could have used a matrix structure along with this A1 tilde and A2 tilde. Those are allowed in quaternion, this thing, because these coefficients can be essentially 2 by 2 matrices, and this is the condition that they must satisfy. Here with this representation, where I have put in x mu to be the element of identity, and when doing the transformation with some mu, the same mu, then is the identity matrix that's required for this transformation. This is something we found that this matches the BCH formula itself. So after understanding this,
so are you saying that good formula that you
yes,
wrote down there and this are
exactly identical. I tried to check this by hand. I kind of succeeded. Then Dittarko said, "This is all nonsense. You guys are old school. Put everything in mathematics." And then a big zero came out on the right side. So we were very, very happy. Okay. So yeah. So, but in any case, let's just, so, but what about this extra degree of freedom of choosing these coordinates and associating something with identity? And it turns out that, this is a very useful freedom, because now think of, I have a Q0 where I associate X0 with identity, and I have a Q1 where I associate X1 with identity. Then these two are related simply by this, okay? And therefore, if I want to, so, and now think of, I am making a transformation. And I have done this transformation in the following manner. Okay, so this is my transformation matrix V, and this is the thing. But now, suppose I would have wanted what happened if I choose my quaternion matrix so that X0 is associated with identity. What would this transformation do? And it turns out it's relatively simple. So you can just write this Q1 in terms of this Q0. Okay. And then you see that it's analogous to associating Pauli matrix structure to these different A1s, B1s, etc. Okay. So it turns out that if you know the right Pauli matrix to associate with these elements, you don't need to choose the initial basis, or conversely, if you choose the initial basis such that the projector index mu is same as the coordinate x mu which you associate with the identity, then you need to choose identity with all this A1, B1, etc. But as you go along and as you make this transformation with different Hamiltonians, this property becomes very useful. It's just a calculational tool, but it simplifies life. No. This is my choice. Okay. Now, suppose I would have associated X1 with identity, but I am doing the transformation with, let's say, D, K0, and P0. The question is, what would be the transformation? And the answer is that, well, I'm going to find the transformation by associating X0 first, because then I know I have to associate just this ABC, etc. here. And then write this Q1 in terms of Q0 and find out what the transformation is. And that is analogous to associating sigma 3 with A1, sigma 2 with B1, and so on and so forth. So all I'm saying is that this freedom can be used. It's actually the freedom of choosing what 2 by 2 matrix you associate with each of these coordinates, each of these parameters A1, B1 in the quaternion transformation.
You have fourfold.
Sorry?
So you could choose, X not to be identified.
There are many choices.
Yeah.
Yeah, sure. There are many choices. But in each case, I have this relation. So that's the idea. And now let's come to Fluke drive. Okay. So now first I consider a two-step Fluke drive where I drive a square pulse protocol where I drive H1 with some H1, which is this mu equal to 1. So D, K1 and P1 forms the Hamiltonian. And then H0 where D, K0 and P0 forms the Hamiltonian. And then I want to make this transformation. Okay. And then what I do is that I compute this, and it's a somewhat lengthy calculation, but one can do this. And then arrange this coefficient as a matrix. Now, it turns out that the eigenvalue of this coefficient is going to determine how my coordinate transformation is going to go in time. And these eigenvalues, it turns out, just depends. So if you had these A1s, B1s, etc., after some algebra, you can see that this depends on the real quantity of A1. Okay. So there are 3 types of response again. So if your real A1, A2 is less than 1, the response is oscillatory. That's like the non-eating phase. If it is 1, then it's a linear function of the number of cycles. That's the parabolic line. If it is greater than 1, it's again exponential. So we had an expression for the phase boundary for that particular drive, but and here is a plot. So if you fix your parameters beta 1 and beta 0 as a function of T2 and T1, this is how the oscillatory region, which is the blue, and the heating exponential region, which is the heating, that comes. Okay. But instead of 2, now if you go to 3-step cycle or multiple step cycle, it turns out that almost entire region is consumed by the heating phase. Okay, the oscillating phase is very, very hard to find, and so we have tried, but we didn't find any elliptic phase where the eigenvalues are pure phase. And so multiple drives in this kind of language essentially almost always heating phases. No, in 2D, the point is that I didn't have an analog of this multiple drive, but what I mean by multiple drive is that you use these different KIs and PIs that didn't have an analog in 2D. So this is specifically for higher dimension. And this is just the phase diagram after one drive cycle, so it hasn't got to do with anything with it. Because it's really the eigenvalues after one drive cycles that determines.
So this is in 4D. You have 3 different spatial things.
Yeah, but you could do it in 3D as well. Just set one coordinate to 0 and this is going to. In fact, if you set 2 coordinates to 0, this is going to give you like 2D. Yeah, so this is pretty general.
Why is this the preferred phase?
Why is it the preferred phase? Because the phase is determined by how the coordinates transform, right? Whether that coordinate or rather, any specific correlations, whether it go, see the correlation functions are tied to coordinate transformation, right? And therefore, if I can find out how this coordinate transform, whether it goes exponentially or it, goes oscillatory, this thing, that's the signature of whether the phase is, yeah. So what I have done is basically find out the net coordinate transformation coming from here, okay, from the coordinate, and its eigenvalues is what determines how the coordinates transform.
So in a sense, you're doing multiple coordinate transformations. Right?
Yes, and that's why there are these A1s, A2s. This is a 2-step drive.
Right. So if you make it more, this used to give you the.
It just, the heating phase just encompasses everything.
Yeah, that's, is there any other way?
No, you could have had the oscillatory phase as well. I didn't know beforehand that the oscillatory phase won't be there.
Yeah.
That's sort of what we found.
But one should be able to trace it from the coordinate transformation.
That's what you do. That's what you do. We trace it from U, the coefficient of U, which essentially
so
goes.
just, that part just and sort of dies away.
This part
should die.
Why it should die away? This, I don't have a good physical understanding of this. So we just saw that when you do multiple drives with different KIs and PIs, it seems that the heating phase completely exhausts the phase diagram.
In the 2D case, everything is sort of like a usual sort of
right.
conformal
So,
transformation. And
one thing you can see is that here you see that there is this real A1, A2 that come in.
Yeah.
These expressions become very complicated, and to find a pure phase out of that is much harder because you have these different elements, in different. So that's the only thing. But I haven't really checked it to that detail to see exactly how it comes in. Okay. So that's that. And the other thing that I would like to show you is that we could again compute this unequal time correlation function. One interesting thing that happens here is that once you compute this correlation function and plot it as a function of angle, okay, you see, we were just using this Hamiltonian with D, K, and P. So we are not using the angular momentum generators at all. But because we are using 2 different K's and P's, the angular momentum generators come in the Fluke Hamiltonian, if you could compute that. And therefore, you have a broken rotational symmetry here in some sense. It's not rotational symmetry. Because, if you have 2 different sets, then of course they are commutators. If you just think of the BCH formula, would give you some L, and that's going to shape the behavior of this corridor. Okay. So this is another thing that we found, and so there are more results. There are also classifications and all that. But if you are interested, I will leave you to the paper, because yeah. And instead, let me just go into this last part of it. How much time do I have?
20 minutes.
Oh, okay.
25 minutes.
Good.
Then maybe I can ask a question.
Yeah, sure.
So you are always
You can always ask a question, even if there is no time. No problem.
If there is, you are always using just these SU11s, one at a time. But in principle, we have this bigger conformal group. There are some bigger subgroups.
That's right. So if you get two SU11s, which are different, two different SU11s, that cannot be subsumed in any SU11 structure.
Sure.
They are going to certainly, get to the bigger conformal group.
Yes.
Yes.
But then why can I not just use different representations instead of poly matrices, some matrices that
Oh, you can.
represent a bigger thing?
Yeah,
and
you
then
can. The computation is a little more difficult.
But
That's
that's
all. In fact,
for new, because you see what happens is that what is called drive is essentially moving in a loop.
yeah, exactly. Yes.
So, and it's a one parameter family. Right. Always. I can always rotate things and put it in one S1. So after all, it's one parameter.
But if I want to do sequential drives along different directions, then I'll have more freedom, right? Because I can select.
Yeah, that's more freedom, but that's going to access the entire group.
Yeah, but
Yes.
the problem might be that this might be not be made. See, the problem is when you talk about evolution in the loop manifold. I don't continuous thing. It is to continue. Suddenly make it going from one to the other, may not have that problem.
No, not really.
Generator of the time translation.
No, but see, that's where the Fluke Hamiltonian comes in, right? I mean, if any time-dependent problem in quantum mechanics, you do this. Essentially, because you change the Hamiltonian as a function of time. You could do a square pulse, time won't be continuous, but you still have your Fluke. There is no problem there. At least in the standard quantum mechanics, there is no problem. I don't know if anything subtle happens here.
Because the group manifold, if I just suddenly make discrete terms. Whether
But the group manifold in some sense is that of SU2, right? No. So the group manifold is something similar to SU2. It's SU11, but in general, this thing.
SU11 is.
But people have looked into this and, so this
No,
is.
he's not asking about SU11. He's asking about the local flow.
No. So that's the thing. If you take two different directions or three different directions, then to represent it at one go, you have to go to the.
Remember that when you write Lorentz, SU11 and SU2.
Yeah.
Just semi-direct product, we identify the identity.
Yes.
So
Here it's D.
carefully making that kind of transformation, you be careful that you don't go beyond that.
Yeah, but it seems that.
Generally, one can do that.
Yeah.
It's not very as general as you want.
Okay. No. Yeah.
On the
Hamiltonian is what? Tridiagonal. What do you mean? It's a 2 by 2 matrix. No, in what represent? So it's a sigma x plus I sigma y, let's say, something like that. Yeah. Why is it? What do you mean tridiagonal? It's a 2 by 2 matrix. No? Sorry, can you? No, but it's a one single site. You see here, I don't have I mean, when I map these generators into this SU11, it's one sigma x. See, in a spin chain, you have to have that index J and then there will be coupling and all that. That's not here. So in that sense, it's not tridiagonal. It's just a single 2 by 2 matrix. Okay, let me get into this entanglement and okay. So here the first part is something taken from some Cardy's this thing. And the reason I want to basically get this, you guys all know this, but the reason I wanted to basically get through this is that later, without saying much of, bringing much of algebra, I'm going to use this language to get this entanglement asymmetry. So let's just refresh our memory. So if I want to write down a density matrix of a quantum system, I can write it as a path integral with this delta function, which tells you the value of the field at 0 and beta. That's a standard thing. Now to get the partition function, what do? I identify phi x prime with phi x, and then in the geometry language, this is just rolling it down and making it a cylinder. Okay. So now if I want to compute the reduced density matrix, I need to identify a region within this entire space where I can define, which is defined as my subsystem, and that is like having a cut in this cylinder. So if you have multiple regions, you will have multiple cuts, but a single region is like a single cut. So now in this reduced density matrix, if I want to compute n copies of them, what I do is that I have this multiple copies, Okay, and I need to basically sew this cards along the end of the subsystems. The rest is of course identified because I don't care about what is outside the subsystem. Okay, and therefore I have this boundary condition on the fields that phi j is equal to phi j plus 1. That's the so. But you see that this is like writing an integral in complex plane with some boundary condition, specific boundary condition, right? But typically, this kind of global symmetries, which comes from this boundary condition, can be implemented in terms of what are known as twist fields. Okay. And these twist fields, therefore, this reduced density matrix can be computed on a complex plane as if the complex plane has some additional twist fields at specific locations. And then whatever expectation you want to calculate there, you can do. So that's the idea of this generation of twist fields to compute entanglement. So naturally, to compute this, since I have to compute the partition function, I need to know the operator dimension of this twist fields. And that's the thing that Cardi pointed out. So how do you do this? So the step one is to have this interval uv, which is my subsystem. And then you map it to the half line by this transformation. So one point goes to 0 and the other goes to infinity. So it's really the half line. And then you map this n Riemann sheets to the complex plane by this transformation, and therefore now the first thing you do is to find out what happens to the stress tensor under this transformation. And this is reasonably simple to calculate because the stress tensor expectation on the complex plane in the ground state is 0. And therefore it's only the Schwarzian derivative that comes in. And you can compute this and it gives you this result. Okay, in terms of this BL. Very nice. But now you see that expectation, the expectation of the twist operators that you have computed must be equal to the expectation of this twist operator in the presence of this, expectation of the stress energy tensor in the presence of these twist operators. And therefore this equation needs to be satisfied. Now the left side of this is just OP of this twist operator with the stress energy tensor. And assuming that they are primaries, okay, I can evaluate this and then demand that this evaluation gives rise to that. Okay, and if you do that, you just find out that the correlation of this must go as Dn, where Dn is this by. It's a reasonably straightforward calculation, but this is what allows you to compute entanglement in generic set. And I wanted to say this because this is something that we are going to use for also computing entanglement asymmetry, where it will be a slightly more complicated setup. Okay. Very nice. So also, people have looked into entanglement of given CFPs. And what they do here is that, first of all, computing entanglement from a state which is a primary state, is quite difficult because it involves 4-point correlations and cannot be done exactly. However, you can use a strip geometry, which can be mapped onto a half plane. And there, of course, the drive doesn't keep the ground state invariant because there are boundary states and stuff like that, which is not invariant under the action of the drive. And there is a specific way of computing this. Okay, so I'm not going to go through the details of this. You can really go through this paper which shows how to do this. But the idea is first to map from this strip to the complex plane, where there will be additional branch cut because of these boundaries. And then there is a very clever deformation of contour which allows you to compute the dynamics on that complex plane. And then you map back to the half plane from there and compute all operators' expectation value on the half plane. These are the 3-step process. And that's what allows you to write down this trace of rho n in terms of expectation of the twist field. So once you do that, what you find here is that you can again find out what the entanglement is. And this is what they have done. Essentially, the entanglement grows linearly in the heating phase, grows as log n if you are on the critical line, and it's an oscillatory function if you are in the non-heating phase. Okay, so these are the 3, and this just comes out from this computation. Okay.
I mean, they really compute the von Neumann. They put this log, this total sending n to 0 or whatever.
You can so this behavior doesn't depend on whether you compute Renai or von Neumann.
Okay.
And actually, the way they compute is basically taking this trace rho to the power n and then take the intending to one limit at the end of the loop. Calculating von Neumann from scratch is really, really difficult. in this kind.
What is N?
Sorry, N is the number of drive cycles. That's like the time. Okay, stroboscopic, but it's the number of drive cycles. And M is the mth Renai entropy. So, okay, so now I'm going to just talk about this evolution of entanglement asymmetry. First, let me define this quantity and why people have been working on this. So when I consider a quantum system, I can write down a density matrix, which is given by the outer product of some wave function. This can be ground state or any other thing. And then, I take this density matrix, I compute my reduced density matrix, and if I represent this reduced density matrix in some basis, I can identify, let's say, a particular symmetry sector, like the number or some other charge or something. And then rho A, in a cartoon picture where it looks like this. Some elements of this are within the symmetry blocks, and some other elements are outside the symmetry blocks. And these other elements are present if the initial state doesn't respect the symmetry. Fine. And then, of course, I can compute my density matrix from here. Well, that's straightforward. But one can do something else. One can compute the density matrix of a projected entanglement entropy of a projected density matrix, where you project this thing into the symmetry sectors. Okay. And then you compute its entanglement entropy by computing the reduced density matrix. So here, this rho A cube is the reduced density matrix for the projected this thing. And you see that these external dots are absent. It's just okay.
That pi is a delta function.
Pi q is a delta function which projects to a given symmetry sector with charge small q. Okay, that's a.
So you have some continuous globals.
Yeah. I'm only going to talk about continuous globals. U1 are mostly U. Yeah.
So how is it different from starting from some state which was in this 20 seconds?
No. So let me just, sorry, I should have clarified that. So the idea is not to know the starting state. The idea is that suppose you have a starting state and you want to quantify how much the degree of symmetry breaking of that state. Okay. So, and that's where this entanglement asymmetry comes in. Let me just get into that. Okay? So now I can also compute the Renai entropy of this projected thing and subtract it out from the total Renai entropy. Now, this part essentially is definitely due to the parts of this rho A which was outside this, because I'm just subtracting these things out. And therefore, it gives you a measure of how much the initial state broke this symmetry. Okay. Now, there are two properties that if the state didn't break any symmetry, then of course rho q is rho and delta Sn is 0. And that's sort of the case where, the system preserves the symmetry. And delta Sn is always a number greater than 0. That one can show.
So
Yeah.
suppose there's an initial state and you want to see to what degree it breaks the symmetry, you can just define an operator and take its expectation.
Yeah, but sure, you can do that also. But this is another method of.
It sounds more complicated.
But it doesn't depend on the operator that you are using. Okay, and also dynamically, this is very nice to see dynamic symmetry distortion. Well, I don't.
States are good.
Yeah.
State good.
It's a state property.
You see that pi square is like.
I think if you do the integrals, you're going to. One should check.
So the way. Yes, matrix. Here is like some kind of.
It's just this projection. It's just this projection. Pi.
This kind of structure.
If you can identify the symmetry and the charge operator associated with it, you can always use this to project the density matrix to that sector. Because it's a projection operator. It takes the state and projects it to that.
But I think the way Vijay is trying to say, if I take the state in this sector and calculate the.
No. Then of course this is delta Sn is 0.
No, but if I compute the relative entropy in that sense.
What do you mean relative
The
entropy?
relative entropy is I have to know the density matrix of the two different states and not just calculating this rho or rho.
No. So you want the entropy of two different states. That's what you are saying.
But here also I'm
No,
computing
I am
the.
no. So here I'm computing two things. One is for the same state. One is that I take the state, compute its calculate its take its reduced density matrix, compute the entanglement. The other is I take the state, project it to symmetry sector, compute the find out the entropy corresponding to that, and then I take the difference, and therefore it tells me that how different this delta, how big this delta Sn is, because it's a monotonic function. It will tell me how much symmetry is broken.
Several states will project into the same state, right? I mean, you know, there can be.
What do you mean?
I
Same
mean,
sectoring.
I mean, there are several symmetry local states. So.
No, I'm talking about a single state and then computing the property of that. There may be several states. For each of these, when you compute, you will get an answer for delta Sn.
That's correct. So, but you know, when you're comparing, this is I'm following what you're saying. So if you take, you know, let's say given a state, you do this process.
Yes.
And you know, if you do it like for a few different states, then the thing that you're subtracting, you know, that
No. For
will be the
each of them, you have to compute an Sn and an SQL.
So what I think what Miller is trying to say is that the projected Sn that you're going to compute, the projected state, that may be the same for various states.
I mean, you.
No, but
it's like a reference.
No, but the point is that no. So, but the point is Sn will be different, and therefore delta Sn will be different.
No, that is right. He's also
Yeah.
asking about sort of something that something that is for a relative answer, right? Because I mean, one of the
No.
state will be same, but
Yeah, it can in principle, but usually at the level of computation for the systems that you looked into, usually this is Qn is different when the states are different. If you choose it properly, at least for simple models. So we have checked that, but in principle it can be. I mean, I'm not saying that it cannot.
And if I have a state, when we're looking at the symmetry sectors,
Yeah.
it might be a tensor product.
sure.
And then I can integrate out and compute just the linear of your tensor product of test out and that's it. It looks like the modernicity of the.
Yeah. Okay. So now how to compute this? The point is that, so suppose I take this and I compute rho q to the power n, that is rho a q to the power n, okay? Then I'll have n such factors of pi q. And if you do a little bit of massaging, you would see that this can be written in terms of rho a times e to the power I alpha prime q out here. And this alpha prime is just the difference of the this value of alpha in successive Riemann sheets. Okay. This again, you are thinking of it in Cardy's picture, but now what happens is that each of this each of this Riemann sheet has a flux threading through it, which is given by this e to the power alpha. Okay. So that's the geometric interpretation. Here, to compute this symmetry resolved entanglement, you need an additional flux insertion. And this is typically done by a primary vertex operator of the CFT. And this insertion is essentially done. It can be done at any place because all I care about is the flux, but it's typically done at the edge of the subsystem so that I can fuse my twist operator with this flux insertion operator and define a composite twist operator in terms of which I can write down the entropy. And this is a work of Moshe Goldstein and Sela, where they showed that this composite twist formalism works.
It's like putting that constraint on that sheet.
That's right. Rather, I would think of putting a flux through each of these in-sheeted Riemann factor. And the only thing which comes in is this extra integrals when you sum over all such fluxes. Fine. So, okay, so let me go through this. So in a CFT, the flux insertion is implemented typically by a primary vertex operator. And one defines a composite twist operator, as I just mentioned. Okay. And this now the task is to compute the scaling dimension of this composite twist operator. That's the idea. So again, what you do is that you do this uniformizing transformation, which maps your subsystem to half-line, just like this. But now you have to be a little bit careful because you are now on a complex half-plane rather than, because you're talking about a strip geometry. But those can be taken into account. But the real thing is that now when you try to compute this expectation of the stress energy, it turns out that the first term gives you an finite answer. And that's because you have inserted this flux through the presence of these vertex operators. And of course, the Schwarzian derivative does its own thing and gives you an answer.
So it's not any more in effect.
Exactly, because you have inserted this flux, right? That's like having a vertex operator. And the answer turns out to be that this part gives you this delta alpha j, where this delta alpha j is essentially the dimension of this operator with which you insert this twist. And the total dimension now gets an addition from this delta alpha. You do exactly the same calculation that Cardi did, which I showed before, and this comes up. Now what happens is that now you do all this OP of the twist operators and compute what this thing is. And it turns out that you get this factor, and which depends, of course, in this dn. So this gives you the symmetry result part of the entanglement. And when you compute delta S, where you subtract this out, because of this log structure, what happens that this part drops out. Okay. And it's only the dimension of this composite twist operators, I mean the primary the vertex operators, which essentially determines this entanglement asymmetry. Now, this is of course natural, because if you didn't insert any, this should be 0, right?
Yeah, how did the log go? There was the overall log, you have that.
No, the overall log is there. I mean, there is a log outside all these integrals.
Yeah, so how? Okay, so you are computing this correlation flow actually.
So there is a log.
Directly from the correlation.
Yeah. I'm just computing. So I'm computing trace rho to the power n directly from the correlation and then writing it. Because there is this division, this thing goes away because it's there in both. And simply you have this.
Yeah, so it's very interesting. Because of the log, you see, the thing inside the log is like a modular axial strength.
Okay. Okay. We can talk about that later. I don't really know. Okay. So now we have to evaluate these integrals, and that's the main. So the point is that to evaluate these integrals, we need to have the dimension, the alpha dependence of this delta. And there are a class of theories where this just is very conveniently quadratic, in which case you can do these integrals exactly. Now the point is that to do this integral, there is a really nice this thing. So you see that this is like alpha j minus alpha j1 squared by 2. So you can write it as some matrix times some vectors. Interestingly, this matrix is same as, me being a condensed matter guy, I must say it in that language. It's free particles hopping on a lattice with hopping half and chemical potential 1. Because the diagonal elements of this matrix is all 1 and off diagonal is minus f. And these technically are called circulant matrix. Their eigenvalues are all known. And interestingly, what happens is that when you put j equal, so there are these n eigenvalues, and when you put j equal to n, one of these epsilon is 0. Which means that when you do this integral, one of these integrals, if you go to the right coordinates, that is transforming into these betas, the diagonal basis, one of this integral is just going to give you 1. And the rest is, what did I go? The rest is going to give you a factor of 1 minus n. And this 1 minus n factor precisely cancels the 1 by 1 minus n factor to give you a kosher entanglement asymmetry, which doesn't depend on any. So, and actually the answer turns out to be log of C naught L over this thing. And this is something that some other group also verified using a completely different formulation, which me being a condensed matter guy doesn't understand. So, and now we need to go to the driven part of it. Again, I'm not going to bore you with details, but one can do exactly the same trick that one did for the entanglement calculation. Because, everything is in the same language. It's just this coordinates that changes because of the drive. And once we do this, let me just forget. So what we find is that as a function of mu naught and t, this entanglement asymmetry essentially has 3 types of properties. So if your drive is such that your system is in the heating phase, and this is, we are in d equal to 2, so I can meaningfully talk about heating, non-heating, and other phases. If it is in the heating phase, your delta S goes as log N. Then it grows. If it is in the critical line, it goes as log n. It grows, but very slowly. And here there is a constant small oscillation. It doesn't really go, it goes close to zero, but maintains this small oscillation. Now let me relate this, and I'll take just one, how much time? Minus 10 minutes?
5 minutes.
No. So, okay, I'll just take 2. Let me just. So, what we also did was to compute these quantities for a standard Ising model, a driven Ising model. There, you would see that no matter where in my parameter regime I am, my entanglement asymmetry always decays, and it either saturates to a finite value if your Hamiltonian doesn't respect the symmetry, or it goes to 0 if your Hamiltonian, the Fluke Hamiltonian, does respect that symmetry. And by symmetry, I mean it commutes with the charge operator, which. However, in this case, this heating and critical line, this is one of the examples where this entanglement asymmetry grows with the number of cycles. And this is something which is different in case of CFTs. I haven't. So we have looked into specific models which are both either integrable or non-integrable in standard quantum field theory or spin chains. There, it's always a decaying function. This is an example where this thing grows, and this I think is somewhat unusual.
That is also a function of temperature. I can see the plot.
It's a dry period. It's not temperature.
The next one. You know this. So
I don't have a temperature anywhere.
so this one, this lattice calculation.
This is MT. This thing is the number of T is the dry period. Everything is at 0 temperature.
But you know, there's a dry, but
Everything is at 0 temperature. It's just the dry period.
but then
Okay, because you drive, the system grows, so you can effectively think of the system being at a given temperature and all that. That's another story. But the calculation and also this analysis, everything is done.
So, but can't you like keep the thing at a finite temperature and still drive it take time and like keep a.
No, in principle, see, the point is that in principle, of course, you can, but see, how do you define temperature in a non-equilibrium system like that? You have to define it in terms of a density matrix, and okay, if you want, you can choose your initial density matrix to be one at some finite temperature with respect to some Hamiltonian.
Because 0 temperature is very far away from so
No, why? You can be at critical point, at a quantum critical point.
Oh, that's
0 temperature. No, I'm not doing that, but you can be. I mean, that's not. But you see, the equilibrium critical points are not that important because you are driving, you are accessing all the states in the in the Hilbert space. You know, the equilibrium properties do not really play that much of a role here. I mean, for a standard integrable or non-integrable Hamiltonian.
I think I'm being right. Here this calculation is for a CFT, right?
No,
So
this is for a CFT.
You'd expect when you do the lattice calculation,
Yeah, no, that I understand. But the point is, okay, so the problem is that if you are doing a standard Hamiltonian from a lattice, you need to first figure out what to drive. Okay, and typical things that we drive in a lattice, such as magnetic field or other things, those are not very simple parameters in CFTs usually. And this drive doesn't correspond to those kind of things. Those are the drives which are typically going to generate a scale and take you away from the CFT. Okay, so and that identification is one of the challenges. At least in my mind, I don't know if other people understand it very well, but at least in my mind, that's one of the challenges.
So this thing, therefore, is not really like a contradiction or anything. The fact that
No, it's just a different drive which gives you this feature, which is typically not found in other ones. Yeah. Okay, so to summarize, I've told you some trivial stuff about dynamics and entanglement, and so the interesting thing about this dynamics is that it's possible to do this in d greater than 2, and actually, the thing to see is whether it's relatable to any of these lattice theories in any way, and that's something that needs more work. So I'll stop here and thank you for your attention.
Since you made this comment about lattice theory, if you take operators on the lattice and drive it, of course, you will generate all kinds of operators in the CFTs, right? So
Right.
it's very hard to imagine.
Yeah, it's very hard to imagine. But the question is there a window? I'm going to generate it, but generate it at different time scales as I keep on driving. And the question really is if there is a window where you see this kind of behavior. That's something I'm not sure of.
One more thing is, so you said that the critical line, one could think of it as an iPhone crossing.
Yep.
Is there any you want to explain? And
Okay.
Is it something that's clearly when it's not
So if you look into this evolution operator in the language of matrices, Pauli matrices, this typically occurs as beta equal to 1. So if you have your Hamiltonian to the sigma x plus I beta sigma y, sigma z plus I beta sigma y. Okay, you see that when beta is equal to 1, this matrix is a Fermionic realization, right? And there you can think of it as having some particular velocity, which is the light cone velocity. If you want, you can think of it in that language. I prefer to think of it as, this is one point where all exponentials become linear. When you exponentiate this matrix, you are only going to get the results.
finding like horizontally including where will it be an interesting question to understand the entanglement dynamics for arbitrary time in this?
Yeah, it will be, of course, sure. But the point is that
if you want to use
yeah.
CFP.
So the thing is that something that I pushed under the rug is that when you take this, so for example, if you want to do it for the cylinder, okay, then you can work directly on the complex plane. But the point is that you need to evaluate a 4-point distance. Okay, because if you are starting from the vacuum, then the two twist correlators, that's going to give you always it's like an equal time correlation function, which is trivial in vacuum. Your S is going to be S0 at all points. Now, the next thing you can do is to sort of put this on use your starting state, which is some primary this thing. If you do that, you have to compute a 4-point correlator. And now the entire data of the CFT is necessary, and you have to most likely do some perturbative techniques, some blocks or something like that. Those are difficult computations. With DeepTarko, we did part of this for large C CFTs, but it doesn't give anything which is strikingly, well, it was not very striking in the sense that the growth and other things were somewhat similar. The other thing that one can do is to go to the street, where you can start from the vacuum of the street. But there the point is that first you need to map it on the full complex plane, which will have a branch cut because of this. And then one needs to deform this contour to evaluate the, so you want to evaluate something like U dagger OU on that plane, right? And that evaluation requires some complicated contours, which needs to be deformed. Now, when it's a standard square pulse type protocol, I know how to do this. And this was done in this PRX paper, but this is where the bottleneck will be. For a generic drive, how do you do that? That's the second thing. But apart from this, yes, I mean, these are the bottlenecks, but other things will be. So, for example, one of the really interesting things would be to do it for quasi-periodic drives. If you take a Fibonacci or other sequences, how would these things go? There are bits and parts of it is done in the Soshpin's paper, this PRX paper, but still there are a lot of things that has not been.
But there is one technique which might be useful is that if you take a field theory system on a 2D,
yeah,
and then take one parameter of the field theory,
yeah,
let's say mass, and you try it,
yeah,
but you started with the flat geometry.
Yes. Yes.
Have put the field theory on it. Now the parameter is time dependent. But it's a property of 2D geometries that you can always write it in geometry as a conformally flat limit.
Sure. Yeah.
So the time dependence or whatever dependence you have in the field theory on a flat space can be transferred to a wide factor times of flat space. And
I
the
see.
field theory becomes trivial.
Okay.
With constant mass. So this is somehow this co-work is with swimmer users to clear the reaction. So how much of the difficulty that you are suggesting can be overcome by going back?
That I don't know. I know that Shumita and Diptarko
Yeah.
worked on this kind of stuff quite a bit, but that was just for the Quench protocol. Actually, I haven't looked into the periodic drive of that. Maybe it would be interesting. I don't feel having looked into it.
Okay, so let's
Yeah.
close the session for now.
Thank you.